So we are continuing with a study of linear algebra, and we are on linear dependence and independence. Okay, so let's go through the basic definition of that, and we'll take some examples that'll help you to determine whether a given set of vectors is linearly dependent or linearly independent. Okay. Now let V be a vector space. So over a field you have your vector space, your big vector space, and then you take a subset of vectors. So and a subset S being part of V is said to be linearly dependent. So this is very key. Linearly dependent here. If there is just distinct vectors, and this is very crucial as well, the vectors should be distinct. In V, so all the vectors you have, little v1, v2, all the way to vn, are all vectors in S. And scalars, so these scalars can be the same, not necessarily distinct, but this distinct part here is actually for the vectors in the set S. If all these scalars are not zero, such that the linear combination of the vectors in the set S using these scalars gives you 0, then we say that says it's linearly dependent. But if all the scalars in front of each vector should be 0, such that this equation will be satisfied, and this is the equation I'm talking about, this one will be satisfied, then we say the set is linearly independent. Or maybe it's linearly independent, maybe something like that. I think the correct word should be linearly independent. Okay, so that is the definition for linearly dependent set and linearly independent set. Okay, now let's go to some examples that we're going to pick and go through them. Okay, so the empty set is what? Is it linearly dependent or linearly independent set? Okay, is it linearly dependent or linearly independent? Now you are saying that you have nothing, so the empty set consists of nothing, empty, like it has no elements. Okay, and I want to multiply this nothing here, that I don't have anything there, by some scalar a, such that I will get 0. What scalar? What should this a be? Because we don't know this, and we are saying that because this is the only member in the empty set is empty, nothing is there. So I pick nothing, multiply that nothing by a scalar, I should get 0. And I don't know this, but I'm saying that the product of two things is giving me 0. So this is algebra here. The product of this and this nothing here is giving me 0. Then it's either this a is 0 or the nothing is actually 0. But this cannot be 0 because we don't know it. It's nothing, so it's not 0. So the only way that this equation will be satisfied is when a is equal to 0. So the empty set here is linearly dependent. Linearly independent. And then this is the argument, because if you pick nothing, the only way, or the only scalar you're supposed to multiply to nothing so that you get 0 is 0. Okay, so a should be 0, and that's the only scalar here. So here it doesn't necessarily mean that you should have two different elements in the set. The only thing that happens here is that whatever number of elements, whether it's just one element in the set, and your linear combination, if you have a scalar multiplying, if let's say you had only one vector in the set and you have a times v1, and then the only way this can be possible is when a is 0, then you have a linearly independent set. And why I did this, or I came back to this, is to tell you that you do not need two or more vectors in the set. The set can be just one vector. Okay, and I have an example of that, so don't worry. A subset S belonging to the vector field, vector space, such that 0 is part of the set. What would you say? Are you going to say that set is? So an example is, you can say S is some arbitrary vectors with a 0 included. Okay, so I have v1, v2, and the rest. Or maybe let's say I have all the way to vn. If you have 0 vector included as a set, as a member of the set S, then what can you say? Here, if you look at it very carefully, you're going to have a1, let's say, times the 0 vector plus a2 times the v1 plus all the way to maybe some an plus 1 times the vn should give you 0. Now we know for sure that if not all these a's are 0, if one of them is at least one of them is non-zero, then we have linearly dependence. If all of them should be 0, then we have linearly independent. Now if you look at it very carefully, we can choose a2 all the way to a sub n plus 1, to be all zeros. But here, no matter the value of a1 we pick, so a1 can be non-zero. If you pick a1 not to be 0, then a1 times the 0 vector is still 0. So whatever you add to, and you choose a2 all the way to a sub n plus 1 to be 0, everything you do here will give you 0. But here, in that case, it happened that, so if you choose a sub 1 not to be 0, a2 all the way to, let me write it very well. So you're choosing a2 to be the same as a3, is the same as all the way to, all of them to be the same, a sub n plus 1 to be 0. Now here, at least one of them is non-zero. And this, if you sum all these things here, because this is a 0 vector, you're going to get a 0. So if you have a subset of a vector space with a 0 vector included, then that subset is linearly dependent, because you can get a non-zero scalar such that when a non-zero scalar multiply the 0 vector, it still gets 0, and you pick the rest to be 0. And that is the definition, right? We said that if such that not all of them 0. So if you have just one of them being non-zero, such that this equation is satisfied, this is giving you 0. When you sum everything, you get 0. Then you have linearly independent. Sorry. Now let S to be equal to just one element, one vector, such that the vector you have is not 0. What can you say about this set? Now let's look at this. For this to be linearly dependent or independent, we should multiply the element we have in the set S by some scalar, and here we have only one element, or one vector, so we can just multiply by one scalar, which is a times v, and we are saying this should be 0. Now you solve this equation to look at what point would this equation be 0. Notice that we know that v is never 0, right? So the only possible way that this product, the product of this thing and that thing, is giving me 0, but we know that one of them is never 0. So the only possible way this can be true is when a is equal to 0, because when a is 0, then you have the equation here satisfies. So this is linearly independent, because the only scalar you need to use is when a is not 0. I'm sorry, when a is 0. Okay, so that is the definition of linearly independent. Let's go to the fourth problem. So that was the third. Fourth one is you have the ijk vectors, the unit vectors along the ijk. If you've done vectors, you know what I'm talking about, but I've given them in terms of their coordinate system. Okay, with this example, let's pick a1 times I plus a2 times j plus a3 times k, because we have three vectors, because this is v1, v2, v3, right? Should be 0. That is what we are looking at. So a1 times I is given by 1 0 0 plus a2 into 0 1 0 plus a3 into 0 0 1 equals 0. So if I do multiply everything, I'm going to have a1 here. So if you look at this, I forgot to mention that, but this 0 that you are having here is the 0 vector. Actually, that is, so it depends on what kind of vector space you are in. So if you look at this is in the R3, the three-dimensional vector space. Okay, and in that case, you're going to have your 0 here will be the 0 vector, and that 0 vector is given by 0 0 0, right? So that is what you need to take note of. So 0 plus 0 a2, 0 plus 0 0 a3, and that is equal to the 0 vector, which I'm saying that you can just write it as 0, just like that. But I'm going to use the definition that in R3 this is the 0 vector. So if I sum everything, I'm going to sum them component wise. So a1 plus 0 plus 0 is going to give me a1. 0 plus a2 plus 0, I'm going to have a2. 0 plus 0 plus a3, I'm going to have a3. And that should give me 0. Now this 0, I'm saying that is the same as the 0 vector in R3 because you need to know the vector space you are dealing with. And so if I have two vectors, a1, a2, a3, with these components equals 0, 0, 0, then this from equality of vectors is true only when a1 is equal to 0, a2 is equal to 0, and a3 is equal to 0. So we pick the scalars from here, a1, a2, a3, and we are saying this is equal to the 0 vector or 0. And through the process, we've been able to show that this is only true when you have a1 to be 0, a2 to be 0, and a3 to be 0. So we have all our scalars being 0. So we have this set has to be linearly independent. And if you take in vector classes, they will tell you that yes, the ijk vectors, they are linearly independent to each other. Okay, now let S to be equal to these sets. So let me name them to be v1, v2, v3. And the reason we started linear algebra with solving systems of equation is it comes down to these kind of problems. Okay, so what you're trying to do is a 4-dimensional vector space. What you're trying to do here is that you want to show that what would happen if I set this equation. What kind of scalars do I have to get? a1 v1 plus a2 v2 plus a3 v3 should be equal to 0. So here the same thing, this 0 is the 0 vector in 4 dimension. So what I'm going to do is going to be a1 into that 1 2 5 negative 1 plus a2 into 2 negative 1 0 3 plus a3 into 7 negative 1 5 8 equals 0, right? And if you do this, you're gonna have a1 2a1 5a1, and then this will be minus a1 plus 2a2 minus a2 0, and then 3a2, and then plus 7a3 negative a3, and then 5a3, and then you have 8a3, and everything should be 0. Now if you sum this, you're gonna have a1 plus 2a2 plus 7a3, so you're gonna have a1 plus 2a2 plus 7a3, and then 2a1 minus a2 minus a3, and 5a1 plus 0, so I'll have 0 here, and I'm gonna just leave it minus or plus 5a3, sorry. I'm gonna have negative a1 plus 3a2 plus 8a3, and this is the final thing that you have. So this 0 vector I'm talking about is the 0 vector in the 4 dimension. So what it means is that two vectors are the same. Okay, this 0 is 0 0 0 0, 4 dimensions. So it means that the first one is a1 plus a2, or 2a2 plus 7a3 should be 0. That's equation 1. 2a1 minus a2 minus a3 should be equal to 0. That's this second term in the 0 vector. Equation 2. You have 5a1 plus 5a3 should be equal to 0. Equation 3. And then the last equation will be negative a1 plus 3a2 plus 8a3 should be equal to 0. Equation what? 4. And then you use any of the systems of equations that we've learned, the method of solving systems of equations that we've learned, to solve the system to find your values of a1, a2, and a3. Okay, this is actually a very complicated problem, but if you solve this system very carefully, you're going to have your a1 to be equal to 1, a2 to be equal to 3, and then I think I have my solution here. Let me try to find it. And then yeah, so a3 is actually going to be -5, I guess. Oh, sorry, -1, I guess. -1. So what it means is that if I put a1 to be 1 here, so in the first equation, you're going to have 1, a2 is 3 plus 3 times 2, that is 6, right? And then a3 is -1 minus 7. So 1 plus 6 minus 7 will give me 0 indeed. Okay. What we've been able to show here is that the scalars that we are looking for, a1 is equal to 1, a2 is equal to 3, and then a3 is equal to -1. These are non-zeros, right? They are non-zeros. So this set is linearly dependent. Like I said, use any of the methods that we've solved so far to find the solution here. Now the C problem, which I think is kind of a bit complicated, is going to be you have the nth degree polynomial. Okay, so there's a definition. You have k starting from 0 all the way to n, and then we have our function defined to be f sub k of x is going to be 1 plus x to the 1 plus x to the 2 all the way to s to the k. So depend on this k value. Okay, now we have a set S defined on the functions f0, f1, f2, fn, and then I want to check whether this is linearly independent or not. Okay, so what we want to do is to pick all the elements in S. Now notice that f0 of x in this S is going to be 1, because why? Because fk of x is defined by 1 plus x to the power 1 all the way to k. But here, if you look at it very carefully, k is what? So this, I can actually talk about it more detailed in this way, that this is supposed to be so this is supposed to be the actual definition of f sub k. Let me write it in a more general way. So f sub k of x, all right, actually is supposed to be like this: k starting from 0 to n, like we have there, then x to the k. In that case, it explains why I have my f sub 0 to. So f sub 0 is going to be k starting from 0, okay, to let me, I think this is yeah, I think I actually defined this wrong. So this side is supposed to be k. So this is k, and this is some I equals 0, and then this guy is also supposed to be x to the power I. Okay, so f sub 0 is going to be k is 0, so it's going to be summation I starting from 0 to 0, right, and then x to the 0. So you just move one step. So I equals 0, and that is the end. Okay, x to the 0 will give me 1. So f sub 0, or the 0 degree polynomial here, is actually equal to just 1. Okay, and then f sub 1 of x is going to be summation I starting from 0 to 1, because k here is 1, s to the I, and that is going to be s to the 0, which is 1, plus x to the 1, that is the last one. So f sub 2 of x, I know you've seen the pattern now, okay, all the way to wherever you want to get to. Okay, so this is how you get to define everything. And now we just pick the elements we have in S, which is f sub 0. So I pick f sub 0 x plus f sub 1 x, some a1, sorry, this a2 plus a3 f sub 0 s sub 2 of x plus all the way to a sub n f sub n of x. Okay, should be equal to 0. Now if I represent, or if I put in every one of them that I can get, every expansion of the general form of if each f, sorry, f sub 0 is just 1, so I have a1 times 1, which is 1, plus a2 into 1 plus x, is it x2 or something, right? Yeah, x, plus a3 into 1 plus x squared, right, plus all the way to a sub n into 1 plus x squared plus all the way to s to the power n, and this should be equal to the 0-degree polynomial. And in terms of polynomial, so I still have my a1 plus a2 into 1 plus x plus a3 into 1 plus x squared plus all the way to an into 1 plus x squared plus x to the n, right? Equals the 0-degree polynomial, which is 0 plus 0x plus 0 x to the power what s squared, yeah, plus 0x3 plus the way to 0xn. So this is not the 0-degree polynomial. This is like the zero polynomial. Okay, let me put it that way. So if you look at it very carefully, this is more like each f sub n has 1 in it. Okay, 1 plus x. So this is f sub 0 was just 1, so we have just 1 here, and this has 1, this has 1. Every one of them has a 1 in them. Okay, let me clean this. Okay, sorry about that. So every one of them has an x in there. So what I'm gonna do here, what do I want to do? What I want to do is I want to just group them. Okay, the ones that contains 1 plus x, a1 plus here I'll have a2 here plus here I'll have a3 here all the way to a sub n, then times 1. Okay, because they will have multiplying 1 and then plus a sub 2 plus a3 plus all the way to plus an times x. And if you look at it very carefully, you're going to go all the way to, so you reduce one variable after each step. So you're going to get a3 plus a4 plus plus an s squared plus all the way to the point where you get to these two point a sub n minus 1 plus a sub n, and then x to the power n minus 1 plus a sub n s to the power n, and everything of these is going to be 0 plus 0x plus 0x squared plus plus 0x to the n minus 1 plus 0xn. So what do I want to do here? What I want to do is I want to compare coefficients. Okay, so if you look at it very carefully, the coefficient of x sub n or x to the power n should be the same as the coefficient here. So it means from this comparison, a sub n here should be equal to this 0 because the coefficient should be the same. So a sub n should be equal to 0. And then from the other part, these two sums should give me 0. So a sub n minus 1 plus a sub n should be equal to 0. This implies that a sub n minus 1 should be equal to 0. Now, if before you got to this point, there would have been a sub n minus 2 plus a sub n minus 1 plus a sub n, and that should also give you 0 because the other coefficient on the other side here is 0. And I know this is 0, this is 0, so a sub n minus 2 should give me 0. Continuing like this, you're going to come to all the way to the point where you get all a1 to be the same as a2 to be the same as a3 to be the same as a sub n to be equal to 0 using the same argument, because you'll be reducing it 1. So from here you reduce it to a sub n minus 3, and you realize that a sub n minus 3 is 0, all the way to the point where you get to a sub 4 will be 0, a sub 3 will be 0, a sub 2, so every one of them is what? 0. So through this we can conclude that then indeed this set S is linearly independent because all the coefficients of the scalars we are dealing with here give us 0. So I mean, this is some of the fun examples you can come across and try to prove that yes, they are linearly dependent or not. So thank you, and don't forget to subscribe to my channel if you have not subscribed. If you subscribe, give me a like and share. See you.